Hello, everyone. My name is Meredith Scott, Marketing and Communications Project Manager at Axtra3D. Thank you for attending this webinar, Concept Injection Molding with Axtra3D's Lumia X1, the BD Journey. BD's journey with Axtra3D's Lumia X1 and BASF's ceramic-filled rigid 3280 began last year and has now evolved since to enable true, rapid concept injection molding. With the goal of going from an idea to fully molded parts in hand within a day capability, the Lumia X1's versatility and this workflow has truly transformed BD's R&D culture. We are deeply grateful for our continued partnership with BD and their willingness to share this process through the webinar. Through our collaboration, we have optimized their workflow and pushed the boundaries for tooling. Their trust and support have been instrumental in driving innovation and achieving remarkable results. Additionally, their findings have been helping our other customers pursue similar goals. Please join me in welcoming AM veteran Brett Charlton, Senior Manager of the Digital Engineering, 3D Printing, and Prototyping team at Becton Dickinson. With over 20 years of experience in additive manufacturing at pioneering companies such as BD, 3D Systems, and Fineline Prototyping, Brett brings extensive hands-on expertise with a wide range of 3D printing technologies. His work in developing and enhancing various 3D printing applications, including concept injection molding, has been pivotal and is the reason we are all here today. Rajiv Kulkarni, Chief Strategy Officer at Axtra3D, and I will be present during the webinar to moderate Q&A and answer any questions in relation to Axtra3D. Please feel free to engage in the Q&A tab throughout the webinar, and we will address as many questions as possible at the end. Thank you, Brett, for joining us and sharing your valuable insights. So without further ado, welcome, Brett Charlton.
Thank you, Meredith, for the warm welcome and the introduction. Hello, everyone. It's a pleasure to speak with you today, and I'm excited to delve deeper into our journey with the Axtra3D Lumia X1 system. Today, we'll explore how this system, coupled with the BASF Rigid 3280 material, has been enhancing our concept injection molding capabilities at BD. You may have noticed and locked on to the term concept in the title of this presentation and wondered exactly what that signifies. My team primarily operates in the concept and prototyping spaces, supporting various R&D needs. BD, a leader in the medical product space, we produce billions of medical components through injection molding annually, and therefore providing our R&D engineers with a rapid method to deliver their designs that has the parts molded in their desired thermoplastics is incredibly valuable to meet their project needs. You may recall that we've been on this journey with Axtra for some time now. Back in January, I had the opportunity to share a couple of case studies where we had aimed to demonstrate how the Axtra3D Lumia X1 printer could revolutionize the tool-making process and truly put the rapid back in rapid prototyping. Rapid tooling is not new to our team. Our team has had the rapid tooling division for years. In fact, my manager was injection molding with 3D printed photopolymer materials more than 20 years ago. The significant breakthrough that we observed with these case studies was our ability to print molds in under an hour. These molds were accurate enough to be placed directly into the press with minimal processing or fitment and allowed us to mold parts in the same day. Additionally, we discovered that by taking a bit more time to incorporate automatic ejection, we could significantly extend the tool's longevity. If you missed that webinar, I encourage you to visit Axtra3D's YouTube page. Ultimately, our initial success gave us the confidence to move forward. Talking about it is certainly fun, but sometimes seeing it is much more valuable. Here's the molding process from the aforementioned case studies. You can see the 3D printed mold tool halves already set in our mud frame, and they're ready to mold parts. The part in question is a simple tip cap with a bottleneck loop and a living hinge. The process begins when the mold clamps the two halves together, forming the cavity that the melted plastic will fill. The molds endure several thousand pounds of clamping pressure before and during the process while melted plastic is injected into the cavity. Injection molding involves high clamping pressures, high plastic injection pressures, air venting, high heat, rapid tooling, and then you rinse and repeat. And there you have it, a fully formed plastic part. For those not for those familiar with this injection molding process, you might have noticed that our cycle time is slightly longer than one would expect with a metal mold. This is because we are using a ceramic filled photopolymer mold for our tooling inserts, which, due to the brittle nature of the material, require a gentler, longer process to avoid fracturing the tooling components. At least that's what we've noticed and observed with our own operations here with this material. So what do I mean by rapid tooling? Well, the slide's title kind of gives that away. The opportunity to turn around injection molded thermoplastic components in a day, going from design to reality or physical parts, is the goal. But let's be honest, not every job is going to hit that target, nor does it need to. So let me redefine it slightly to say that rapid tooling is the ability to remove or minimize the largest bottleneck in the process, the fabrication of the tooling components. Looking at the images here, the gap between image 3, the top right, and image 4 in the bottom left is usually significant. Depending on the complexity, the mold fabrication can take up to 6 weeks. I'm not suggesting that this mold would take anywhere near that long, but you certainly won't have the mold componentry available in 1 to 3 hours like you would with the Axtra system. Another area in the process that can take a significant amount of time is the space between image 4 in the bottom left and image 5 in the middle. That is where the tooling fitment takes place to ensure that the mold components are fitting together perfectly and the process is functioning as intended. This is another area that we believe that harnessing the Axtra3D Lumia X1 system and the BASF rigid 3280 material is proving to reduce time getting molds into the press. It sounds simple, but to get 2 or more components to fit perfectly together to ensure there's no flash at the parting lines is no small feat. It usually takes hours and hours of work to get these halves to fit, but we've seen the tooling come right off the machine and require very little fitment effort. Let's talk a little bit about the advantages of the Lumia system as we have seen them for our molding application. First, there is high throughput. Our case study allowed us to produce the complete mold set in under an hour. And if I had wanted to print another set, it would have fit right on the platform and not added any additional print time. It never hurts to have an extra, especially when you need to dial in your process at the beginning. To date, the largest mold set we have produced has measured around 5 inches by 6 inches in the X and Y by about 2.5 inches deep. That mold half took roughly 2.5 hours to print. So let's take a look at the imaging process of the Lumia system. Notice in the video how the laser takes less time to complete than a DLP cross-sectional image flash. The lasering process being faster than the DLP imaging means that the time driving the process is the DLP imaging, not the laser, as one might expect with the laser-based technology. The next 2 items cannot be understated in the value of the system. The combination of glossy, smooth, super flat surfaces for the parting line and superior overall accuracy significantly reduce the time it takes to get the mold into the press. Let's take a look at what we mean by flatness. You can see here that the surface maintains its flatness from front to back. The claim is within plus or minus 20 microns, but you can see here that the dial indicator is showing less than 10 microns or 0.010 millimeters from front to back on this parting line. Historically, we've had to add stock to the parting lines and back surfaces and potentially even other surfaces and make other allowances that we would then machine away to achieve the appropriate stack height and fitment. With the Axtra3D system, we've been able to eliminate most of these secondary allowances as they are no longer necessary and only add time and cost to the process. As mentioned before, we have gone fairly large with our concept mold inserts, but we haven't even harnessed the full capacity. The system has the ability to print up to 5 inches by 10 inches in the X and Y directions, and the full depth of the chamber is 18 inches, which should significantly satisfy a large size constraint. In the R&D space, cost is not always the driver in what we do, but it certainly helps. And as you can see here, the cost will be driven by the size of the tool and componentry that you need. But the costs are not always prohibitive or not prohibitive at all. With the Lumia X1 system, you get to take full advantage of the hybrid photosynthesis process, which combines SLA and DLP. What you get with this technology is the laser's ability to smooth out the DLP pixelation. Smoother surfaces are always desirable. In the process of injection molding, where ejecting the part from the cavity is a life-limiting process for the mold insert itself, anything you can do to smooth out those surfaces is welcome. In the past, we've spent quite a bit of time either polishing these cavities ourselves by hand or farming that out to an external provider for their expertise. Out of the box, we've been fairly happy enough with the BASF 3280 sidewalls when combined with the Axtra printer that we've been able to eliminate most of that secondary polishing. When you combine all of the above, you develop a process that is ripe for rapid concept injection molding and one that potentially could deliver a new option for low volume production, but one with producing real injection molded thermoplastic components. We've seen upwards of 300 pieces in multiple materials out of our Axtra Lumia printed molds to date, but depending on material, you could get more. And with the speed of mold fabrication accelerated, you can be producing a replacement mold while you're actively molding with the original. Things have been moving along well since those early case studies, and while I cannot elaborate on specific projects and components that we've been molding, I can confirm that we have used the Axtra Lumia X1 to produce mold componentry for a variety of different projects and applications. That includes both with and without automatic ejection, flat and sculpted parting lines, tooling with multiple inserts, and some mold tooling as complex as a jigsaw puzzle. Another area that we've seen success is in fulfilling the role of ejector plates. Historically, our ejector plates in the R&D space get used over and over for a variety of projects, and they eventually resemble Swiss cheese due to all the ejector holes that we've drilled into them. Well, we've been able to retire many of those ejector plates with 3D printed ejector blocks that are specifically for the project. And they add little time to the print process, and they minimize the work our mold technician spends on the overall ejector pin fitment. We have molded with a variety of materials, including polypropylene, ABS, polycarb, and polystyrene. And we've also molded with multiple elastomers, which I'll touch on shortly. We've also produced the largest 3D printed mold sets that we've ever attempted with a photopolymer mold with success. So I do want to mention some tips for success. As mentioned earlier, the key to being successful is how you handle or treat the mold. If you go into this expecting to perform like a metal mold, you will likely fail. The BASF 3280 material is a ceramic filled material, and ceramics are brittle materials. But if you take care of it, it can last many shots. As already mentioned, you need to develop your process based on your shots from the start. Don't overclamp the mold. I'm sure your press can achieve extremely high clamp pressures, but I recommend that you use only what you need to keep the mold shut during the ejection process. Also, if you overpack the part during the fill process, you will likely fracture the mold components. We generally work our way up to the shot size using minimal ejection pressures to fill the cavity so as not to overpack. I lightly touched on elastomers on the previous slide, and I'll lightly touch on it here. I wanted to highlight that we have had success with molding various TPEs and TPUs across a range of durometers. When working with elastomers, you might be surprised by how many successful shots you can produce with a single mold. This is primarily due to the ease of part ejection. Softer materials are more pliable and less likely to fracture the tooling during the ejection process. Regarding the success factors of the Axtra Lumia X1, many have already been highlighted. The system prints with exceptional accuracy and delivers on its promise for speed. The HPS process results in smoother sidewalls, which aids in the part ejection. Additionally, the mold components produced by the machine have a glossy, smooth, flat parting line that, combined with its precision, significantly reduce the extra work required for fitment, leading to cost and time savings. In all honesty, before discovering this application with the Axtra Lumia X1 coupled with the BASF material, we had essentially given up on producing molds using SLA or DLP processes for a myriad of reasons. SLA molds typically take around 16 to 24 hours to produce and required extensive post-printing adjustments for proper fitment. And the materials available to those legacy technology often yielded only a few usable shots before failing. We have also attempted to use our DLP printers by leveraging a handful of our high heat deflection materials, but we ultimately ran into issues. Those issues included trouble with the thick cross-section starving or just not forming during the print process, or warpage or distortion of the thick cross-sections from the print process, or if we managed to actually print the tooling successfully, the materials were overly brittle for the injection molding process, leading to immediate failure. We had transitioned to producing our rapid molds with direct metal 3D printing due to the longer lifespan of the metal printed tooling. The direct metal process wasn't much longer than the SLA, and we were assured of the mold's durability. If you're going to take 2 or more days for mold fabrication, you want to make sure that molds produced will at the very least yield some molded parts that you can provide to the requester. However, the Lumia X1 has changed all that. While we still use direct metal 3D printing, we now have a legitimate alternative that can handle a variety of projects that will enable us to either succeed at a breakneck speed or fail fast. And that's the goal, right? So the innovation has transformed our approach at BD, especially into R&D. Rapid now truly means the potential of going from concept to molded parts in a single day. It allows for quick failures and rapid iterations. If a mold breaks, a new one can be printed fairly quickly. And this means that engineers can iterate more frequently or achieve design freeze faster, ultimately reducing that time to market. You might be wondering about the criteria we used to evaluate the Axtra system. First, we assessed the system's accuracy across the print envelope. And we're pleased to find a consistent precision of plus or minus 25 microns in the XY plane, which was better than what Axtra was actually claiming. Next, we compared SLA and DLP printed components versus those printed with Axtra HPS technology. Hands down, the HPS is faster than SLA, and it delivers a similar sidewall quality. When it came to comparing HPS versus DLP 3D printing, we were happy to see that the print speeds were similar. And while not all parts printed onto Axtra showed visible difference in the sidewall quality to the naked eye when compared to DLP technologies, they were always comparable, and in many cases, we did actually deem them superior. So we also confirmed the system's capability to achieve the advertised 50 micron as a minimum feature size. Our decision to partner with Axtra was based on a handful of criteria. First, there was part quality and accuracy. One thing that my manager has always pressed upon us is that beyond anything else, a machine must produce good parts. But what does that mean exactly? That means, to us at least, that the printed parts must be accurate within the stated schematics from the OEM, and we also must have a way to maintain and potentially even enhance those claims through the use of software tools. The parts also must resolve in a positive aesthetic way so that our partners, basically achieving what our partners expect. The next thing we were looking for was a valid application or a significant material. We needed to identify a compelling application that would justify the machine. And we kind of stumbled into the concept injection molding application, which helped us justify the machine. We also developed a strong partnership with Axtra. It's crucial to us with any partnership that it extends beyond merely purchasing the equipment. We engage in weekly discussions with Axtra's team and have cultivated a robust partnership that benefits both Axtra and BD. One other area that I've not touched on is the material partnerships that Axtra3D has developed in the photopolymer space. We were very interested in the materials pipeline for this system. Initially, we did not intend to purchase the system for concept injection molding, as I stated, but we discovered this potential during our testing. Axtra has actively worked with many of the material providers in the space, including BASF, 3D Systems, Hinkle, Evonik, Spot A, Keystone, Nextent, and among others. It truly democratizes the materials available to us that have been vetted by Axtra to effectively run on their printers. We also greatly appreciate the open source nature of the software and the machine such that we can print with what we want to print with and not be bound by just the material offerings already available on the printer. So there is the ability to develop any material that you want to with their software tools. Using all of this information, we had a strong enough value proposition that we were able to convince our senior leadership that the Axtra3D Lumia X1 was a valuable addition to our capabilities. All right, well, that's it for today. I hope you have found this time together enlightening and valuable. It's been a pleasure to discuss BD's value proposition for why the Axtra3D Lumia X1 has been successful in our R&D space. You can see a few of the value propositions highlighted here. Thank you for your time, and I'll turn it back over to Meredith for some Q&A.
Awesome. Thank you for sharing. We hope you all enjoyed a little bit more about concept injection molding. So now let's jump into some Q&A. We have a few questions. The first will be for Rajiv. It is on the Axtra side. So the first question would be, does Axtra3D offer a fully dialed solution?
Yes, we do actually. So the way Axtra operates, it has two different business models. One is where we qualify materials, process styles, and profiles, and we provide them as fully dialed solutions for various different applications. So that's readily available with any printer that you purchase. And then if you are in the field where you would like to experiment with new processes and new materials, we also have a way for the customers to do that. So specifically for this application, we have fully dialed process styles. Some of them were developed in conjunction with Brett, with BASF, and we've had strong partnership in developing this as a solution.
Great. Thank you, Rajiv. Another one on the Axtra side as well. Can the Lumia that prints mold inserts be used for any other materials and part types?
Yes, the answer is yes. The mold inserts is just one application and one solution that we talk about, but customers have used it for connectors, low volume production, dental applications, and we have several other solutions that we sell with the printer, and they're all interchangeable based on the profile styles and the materials that you would use. So absolutely, and if you have any interest in new applications, just reach out and we'll be happy to qualify those as well.
Okay, Brett, we have one for you. Do you make a specific change to the insert design based on the material being jetted?
The short answer is no. The insert is printed solid, or at least it is today. We have planned to experiment with lightweighting the molds to see if that reduces costs further. But overall, the Axtra plus BASF solution is able to print the solid cross sections very fast and accurately and flat. And that was deemed to be the easiest way to achieve success. If there was a change, I think I mentioned it earlier that we have stopped from adding stock to a lot of the parting or mating features. So that just sped up the process.
And did you make any changes to the actual injection molding process? Somebody asked.
Well, I mean, assuming that you're coming from using metal molds, which we do, we also have, I mentioned direct metal, and we do machine some molds. The process is somewhat different. I mean, and by different, I mean that we try to be gentler than we would be with a metal mold. It's important to understand that these are ceramic photopolymer materials that can support high heat deflection temperatures, but they are not metal. So historically, the chemistry in the photopolymer space, as you get more brittle, the higher heat deflection temperature that you can actually do. And so, and also this is a ceramic filled material, so naturally it's going to be brittle. So you kind of want to treat it a little nicer, and that's kind of how we've gone about it. Basically, we start with a understanding what the precise shot size is, and we start off lower than that. You don't want to fill out the mold on the first shot and pack it out so hard that you fracture the mold. So we kind of nurse our way into it, and similar could be said about clamping pressures. We're not going to over clamp. All these presses have the ability to clamp pretty hard. Even the small ones, we don't need to use all the clamping pressure, just enough to keep the mold shut.
Thank you, Brett. Is there always heat cycle involved before using the molds?
You know, we've done both. The answer is no. In fact, our initial case study did not have any heat treatment. So, I mean, you can certainly heat treat the mold to increase the heat deflection temperature, but for us, we haven't necessarily deemed that of value to the process. So it just adds time for us. So we just print it post-process and give it to our machine shop or to our mold shop.
Okay. Have you tried this process with any other printer? And if so, what were your findings?
Well, I mean, I mentioned earlier, we did, my manager, Larry, he's been in this space for a while. We were 3D printing molds on our SLA machines 20 years ago. And so, yeah, we've had success with it, you know, but it just took a little bit longer to produce the mold inserts. And so, but we had success with that. And then we also, we tried with DLP processes. We just were never able to achieve a fully print. I mean, if we were able to print it, it usually had distortion to some extent, warpage or distortion, or if we tried to get it into the press, it ended up being overly brittle. And so we weren't successful with any of those processes. And so ultimately, we, as mentioned before, we had actually transitioned to metal printing, but this brought us back to actually trying with a ceramic filled mold. To be able to print those molds, and I mean, for the case study that we were printing in under an hour, that's pretty amazing that you can take and print a fully solid block that quickly, and it's still accurate and flat with minimal post-processing.
Okay. Next question we have is, what has been the overall reaction of the IM operator about these molds?
You know, that was interesting because our injection mold lead, he came from a background where they didn't use 3D printing. And it took a little while to get him interested in using metal 3D printing as an option. And then even more so with this, but proof's in the pudding sometimes. And so I think he learned a lot. He was willing to try it. Once he had success, it gave him confidence to try more. So yeah.
We have, is it possible and is there any advantage to using cooling channels in the printed cavities?
Well, we're using a mud frame, and historically we don't have cooling channels in there. I could see you could obviously print those right into it, but I don't know that it would be valuable. We've never done it ourselves, but I mean, it's a ceramic mold, so it's insulator. So I don't know that you're going to be able to cool it like you would a metal mold, or if it would add value. So
Has there been any experimentation with polishing molding surfaces?
I mean, it's similar to polishing any 3D printed part of photopolymer material. You can certainly sand, going from low grit to very high to remove the layer lines, and that has been done, but the surface quality off the machine has been good enough to minimize the need for that. I'm back in my early days, I remember spending hours polishing these things. And we're not doing that with our molds at this time.
Okay. Would the surface quality allow to print perfectly transparent parts, such as an ABS?
Is that for me? Um,
I think
for
so, yes.
for printing, so we're talking about printing, like an ABS-like photopolymer. Yeah, I mean, this the surface, the up-down surface, it's going to come out clear. I mean, that's the surface is touching the membrane as you're printing, and that's going to be super flat. And so if you have a clear material, it's going to be very clear. A lot of times what I've found in clear 3D printing, a lot of whether or not the part is clear has to do with somewhat with the layering, right? So your how much layering you have. All 3D printing is a layered process, and no matter how smooth that is, that does add some level of more translucency than transparency, but also the post-processing, how you handle it. How do you handle the part? And so with the right material, I do believe you could get a really clear part. That's not been a focus of our applications at this point, though.
Brett and Rajiv, maybe Rajiv, you can take this one. Do you see a benefit or need to design in cooling channels to aid with heat dissipation?
Rajiv, you're muted.
No, I said, Brett, you want to take that since you've been using it?
Oh, yeah. Well, I mean, I think we kind of answered that a second ago with another question. And I don't know that there's value in it or not. I mean, because we haven't tried it. It being that it's an insulator, it probably won't be as effective as you would expect for like with a metal mold where you're trying to keep that cavity cool. So, but from my experience, I don't have any expertise on that one.
Yeah, and so I'll just add one point to that, Brett, is we are seeing more and more of our customers now create lattice structures. So instead of having a bulk mold, they create internal lattice structures that are exposed from the backside. One, it makes the mold lighter. Second, it uses less material. So instead of cooling channel, having lattice structures on the backside has helped a few customers that we've seen this in.
And we had one more question that, maybe you can reiterate. I know you touched on it earlier, Brett. What were some initial learnings that we can avoid?
Initial learnings. You know, I'm not with the I was actually pretty surprised at how well these parts printed directly on the platform. The molding didn't require the mold tooling didn't require support structures or anything. So we're printing it flat on the platform and then popping the part off the platform. We kind of went into it with some sort of experience with 3D printed tooling. So we kind of understood what might be limitations. And then we quickly realized that, hey, maybe it's something that we don't have to do. When our molding team didn't add stock to surfaces, I was surprised by it at first, but they were having success. So that was a learning. I mean, with every technology, you're going to have key learnings across the process. We got started with Axtra fairly early, and before they were even launching systems for production. And so we learned a lot in that time period about how to properly support the components and what kind of post-processing is involved afterwards. But yeah, I don't know that I have anything more key to that.
Great. A lot of the questions we have here, we have touched on before, so we can reach back out and reiterate those responses to you all after the webinar. I would like to give Rajiv and or Brett a final word, and I think we're going to wrap up for today. And like I said, any question that we may have missed, we will follow up with you after the webinar.
I'll just ask Brett one question. Brett, one of the common question we get from most customers who are looking at this solution is how many shots can you take in these molds? So if you can sort of explicitly answer based on a few material types that are the common material types, polycarbonate, polypropylenes, TPs, TPUs, just what are the ballpark shots that you take in a mold set?
Well, the way I would answer that is the softer the material, the more shots you're going to get out of it. So if we haven't had a project since we got started with this that went above our initial case study of 300 shots, but we had 300 shots in and that was in polycarbonate and ABS plastic and polypropylene. The polycarbonate is going to be your more problematic material of those three. And so I would imagine that your curve's going to go down with that material, where you might get more with polypropylene as a softer material. And then in your elastomerics, I've been surprised with photopolymer molds and with how far you can go with an elastomeric material. So something in the 40, 50, 60, 70 durometer. And I believe that has to do with the pliability of the molded part, not having some give. I mean, we are again dealing with a ceramic mold, so it's going to be somewhat brittle. And I think some of it, I hate to say it depends. If you have a part that's got a lot of thin features or something like that, that might actually give you a little bit. If your mold has little features that are really thin on it, those areas are going to be the likely areas to fail first. So that's kind of the key there.
Okay. And I'll just add a last question, because this is also something we hear from customers all the time, is some insights into the cycle times. Are the cycle times longer or shorter? What difference have you seen on that front?
Well, yeah, we're doing longer cycle times. For better or for worse, I'm not, to be honest, that's kind of something that is ingrained in us from our early days of working with us. And our goal is to turn around parts as quickly as possible. So we're trying to do anything to not have to put in another mold set. So, but, it's basically, I've heard, I mean, I remember talking to BASF, and they encouraged actually going faster because you keep your ceramic warm and you don't necessarily want it to cool down. But at the same time, we've had success with going with longer cycle times. So, 3 to 4 minutes between shots. But if you don't have automatic ejection, it takes a little while to get that part out of the mold anyway. So you're kind of cooling while you're actually ejecting the part. If you're putting in automatic ejection, then you have to instill like some automated pauses in there. So
Okay, thank you so much. Meredith, are there any other questions that the attendees have asked?
No. I think we've covered most of it. There's a lot of overlap. But like I said, we'll follow up again with those kind of overlapping questions just to reiterate those points.
Okay. Brett, any other last thoughts from you?
No, I mean, I think I hit on it in all the different slides here. It's been awesome. We were certainly surprised when we worked with the with this machine and this material initially. Like we had started with other materials and we just weren't having success. And then once we got to this for this application, it just was easy. And if you remove those barriers, if you don't have to struggle too hard, it just works. That's a beautiful thing. And that's kind of the way it's worked out for us. So I'm not going to say it works for every project, but certainly we've had success in a myriad of them and encourage you to try it. So thank you for your time. It's a pleasure talking to everybody today.
No, thanks a lot, Brett.
And thank you.
We really appreciate you taking the time. I think the partnership has been good. I think the back and forth that we've had over the year since you bought the machine has been quite wonderful, I think. And we have a real way, I feel, that we can bridge traditional manufacturing and additive manufacturing together through this solution. And thank you for your partnership in helping us do this.
Absolutely.
Thank you all. And if
Thank you all.
if you have any other questions, let Meredith know, email us, and we'd be happy to answer those as well.